Hello, my name is Marcus Agun, and this is Lab 1 for Physics 2211. The purpose of this lab was to explore the motion of an object at constant velocity, which is a constant speed and direction. This lab focuses on the application of Newton's second law and possible discrepancies between what Newton's second law dictates and what is actually observed. Newton's second law relates the net interaction of a system and surrounding to observed motion. It dictates that an object will maintain its velocity unless a net force is exerted on it. This relationship is characterized by the momentum update formula, where the final momentum is equal to the initial momentum plus the net force divided by mass times the change in time. But when mass is constant, this momentum update formula can be rewritten as a velocity update formula. So final velocity equals initial velocity times net force over mass times delta t. So the procedure. First, I'm going to be observing the constant motion of a soccer ball. I'm going to put the soccer ball on the ground, put the camera on the ground, record the soccer ball moving across the camera. I'm going to use that video and put it into a tracker. I'm going to mark the position of the ball per frame. Then I'm going to use a tracker to find out the initial velocity of the ball after it was kicked. Then I'm going to be creating a computational model. And in this model, I'm going to just use the GlowScript template, and I'm going to edit the template to where my initial conditions are put in there and my velocity and the conditions like throughout the entire motion. Like for example, the net force on the ball should be 0. And then I'm going to compare the two models. So I'm going to put both of the position over time graphs overlapping each other on the same graph, and I'm going to see how they compare to each other. They should be relatively the same though, because according to Newton's second law, the velocity should remain constant. So they should be relatively equal. So the soccer ball, it was kicked from left to right. I have the origin of my axes right where the soccer ball is supposed to start. So it's like not right when it's not accelerating when I kick the ball. It's not accelerating at the origin. It's actually like already in motion, but just like slightly. So like directly after I kick the ball, so that I don't have acceleration in my data. Then I use the tracker to graph the position over time, and as you can see in the graph, the slope is somewhat consistent, so that implies like a constant velocity, because the derivative position is velocity. So a constant slope on a position graph usually means constant velocity, and the initial velocity for this was negative 1.415 meters per second. So first I set the ball's mass. The mass isn't really important, but I set it anyway because I have a scale, so I measured it to be around 0.42 kilograms. The initial position of the ball is just 0 because that's where I set the origin of my axes. And then I put the initial velocity of the ball to be negative 1.415. And then I put delta t to be 0.03 because that'll give you a pretty accurate time. Also, that matched up with my the time step that I used when I went frame by frame when I observed the ball. So I could get relatively the same time steps as when I observed the ball. And my while loop, I set the net force equal to 0, and I use the velocity update formula. So final velocity equals initial velocity plus force, and the net force is going to be equal to 0. So the velocity should remain the same throughout. And then I use the position update formula, which is the final position equals the initial position plus the average velocity times delta t to update my position throughout time. And delta t was set right here. So yeah, and then after that, advance the clock. And then this is the result. So the result the position versus time looks relatively the same as with observed position over time, at least when just looking at it by itself. And the velocity stays the same throughout, and the model. So that is good. And then computational versus observation. So they're relatively close at the start, but then they sort of kind of begin to like diverge near the end. That's probably due to like some unaccounted forces. For example, in this experiment, we don't really account for like drag force or frictional force. Oh, by the way, the blue is the computational model and the green is the observed. And so yeah, it's probably due to more forces acting on the system that we did not account for. Yeah, and also, so the tracker allows you to look at the velocity per unit of time, and as you can see, it doesn't seem to actually stay constant when I observed it. So that could be like due to the way I kick the ball, or like maybe add some like weird spin on it or something like that. So that could be a real source of error right there. And so how would the results change if I changed the axes? Well, honestly, I don't really think the result would change when I change the axes, because the position or the position vector should still be pointed in the same direction, and the magnitude of the velocity, if it's still the same. So if the magnitude of the velocity is still the same, and the position of the direction of the position vector remains the same, then the axes really shouldn't matter for how the ball behaves, like how the motion of the ball behaves. Like the f net should still remain 0, and the velocity should still remain constant. And I don't think it's possible, at least with the tools at my disposal in this lab, for us to like determine all the like pushes and pulls and net forces on the object at any given time. Like there could be a ton of different things that could factor into how the ball behaves, and I don't think it's very possible to just account for all that without some really sophisticated techniques. Yeah, and in conclusion, I think that Newton's second law holds up decently well against observation, although there's a little bit of discrepancy. It could be due to sources of error in the lab, and also we assume a frictionless surface and 0 like drag force or anything like that. So overall, I would say Newton's law does hold up pretty well.